Hey everybody, so 7.3 did not record from Thursday, so I'm just making a video of it. So the first thing I thought I'd do is this is over the 1324 stuff. So we talked about on Thursday in class on diagrams and tables and something called the multiplication principle. All right, and this is something that is taught in 1324, and we'll kind of work our way through it. So they have this problem here that you're looking for a new car, and if you narrowed your decision down to a Mustang, but you can't decide on the exact color, transmission, engine, or options package. So there are three sizes of engine: 3 liters, 3.8 liters, and 4.6 liters. Okay, 2 transmissions. So I can get each of these in standard or automatic. All right, so if you think about it, for each one of these options, for each one of the liters, I have 2 more choices. So basically, I have a total of 1, 2, 3, 4, 6 choices now. So I had 3 engines, 2 transmissions. So, and then it says 5 colors you like. So I've got a choice of 5 colors for each of those packages. So if you count, you know, this is 5 each, and there's 5 choices, and there's a grand total for each of the choice for each of the 6 choices. So you're going to see 6 times 5. You're going to see 30 choices. So there's 5 choices for color. Okay, so you can see what's happening here is I'm just multiplying by the number of options. And I've got 3 option packages: is GL, Sport, and XL. So basically all I have to do is multiply each of the number of possibilities, and that gives me the total number of combinations. All right, so 3 sizes of engine is 3, and 2 transmission is 2, 5 colors would be 5, and 3 option packages. So if I multiply these together, let's see, this is 6 times 5 is 30 times, you're going to get 90 different options of combinations of Mustang. Okay, so something like this, all you have to do is multiply the combinations together, and that's how many there are. Like, you know, one of the classic problems they ask on this, you know, you're choosing between 3 shirts and 4 pairs of pants. You know, how many different outfits can you form? Well, it's 3 times 4, it's 12. Okay. Now, there's some other options that you have for counting. We're going to look at some different methods. All right. So one method, you know, I wouldn't recommend it because you can just multiply. You got 3 sweaters, 1 cotton wool, and 1 alpaca. You have 4 hats: red, green, black, and purple. And if you want to wear 1 sweater and 1 hat, how many different combinations? Well, we know from the multiplication principle, 3 times 4 is 12. You can also list them all out, which she's done here. You know, a cotton sweater, red hat; cotton sweater, green hat; cotton sweater, black hat, etc. And so, and you can count all of these combinations, and sure enough, there's 12 of them. Now, besides just listing them out in organized fashion, you can also do what's called a tree. With a tree, what you do is, like my first branch was the sweater options: cotton, wool, and alpaca. And for each of those, I have 4 hat options. So red, green, black, purple, and red, green. You know, each of the different colors goes with a type of sweater. And if you read down a branch, like the first branch here would be a cotton sweater with a red hat. So, and this would be a cotton sweater with a green hat, and cotton sweater, black hat, etc. So this list over here, by reading down those branches, gives you all your different possibilities to list them out for you. It can be helpful. All right. Another option, you know, tree diagrams and 2-way tables kind of do the same thing. We can make a 2-way table. So with a 2-way table, I can list it doesn't matter, you know, where I put the colors and the types, but on one way I'm going to put the colors, and one way I'm going to put the types. So red, green, black, purple, cotton, wool, alpaca. And I can just read, okay, like here would be cotton red, this would be a wool red, alpaca red. This would be cotton green. So that would list out all your possibilities. And notice this is 4 by 3. Sure, 3 times 4 different possibilities. Okay. All right, suppose you says you flip a penny and a dime, determine the number of outcomes using a tree diagram. All right, so I'm going to say I flip the penny first. Probably really should have said that. All right, so if you think about it, I have two different outcomes. I have heads or tails for my penny. Now I flip a dime, so my second branch is a dime, and guess what? The dime has options of heads or tails. And the dime has options of heads or tails. So I can look at all my options are, I get heads, heads. Let's see, I'm just reading down the branches. Heads, tails. Tails, heads. And tails, tails. So these are all the different possible outcomes of our experiment. Okay, one red die and one green die are rolled. Determine the number of possible outcomes. Now, using a table. A table is not the most efficient way to do this because I know there's 6 choices for the red die and 6 choices for the green die, so there should be 36 of them. But we're going to make it. We're going to make or start making a table anyway. So I'll let the red die go this way and the green die go down. So, you know, red, you can roll 1, 2, 3, 4, 5, 6. And green, I can roll 1, 2, 3, 4, 5, 6 different possible rolls. So basically, this is, if I list the red, I'm going to make this like this, the red first and then the green. All right. So we can list all the outcomes. So this one, make some 3, 4. So this one, like the red is 1 and the green is 1. Let's see here, the red is 1 and the green is 2. And the red is 1, the green is 3, 1, 4, 1, 5, 1, 6. And then now we're at 2 for the red dice. So it's 2 and the green is 1, 2, 2, 2, 3, etc. Right? And you know, this would be 3, 1. You guys could fill it in. So my point is this lists all the different rolls that you can make. This is also what's commonly referred to as a dice table. Helpful when you're doing probabilities with dice. All right, so we're gonna do some counting problems. We have 2 tennis balls selected from a bag that contains 1 Penn, 1 Wilson, and 1 Dunlop. Okay, so it says the first tennis ball is picked and replaced, and the second ball is selected. So basically, you pick one out of the bag, you look at it, you put it back in the bag, and you select another one. So determine the number of outcomes. So basically, I've got 2 little things I'm going to do. The first time I pull a bag, I have 3 choices, Penn, Wilson, or Dunlop. I put the ball back in, shake it up, and on the second draw, I also have 3 choices. So 3 times 3 is 9. So I've got 9 possible combinations of balls using multiplication principle. All right, so let's do another. Suppose the first tennis ball, this is important because now it's not replaced before the second ball is selected. Determine the number of outcomes using the method of your choice. So what I want you to think is we draw a ball. Now on the first draw, we still have 3 choices, right? Penn, Wilson, or Dunlop. But whatever I pick, I'm not going to put it back in. So on the second draw, I only have 2 balls available, and I don't know what they are, but I've only got 2. So I've got 2 choices now because one of them was not back in the bag. All right, so I multiply those together and I get 6. So now there's only 6 outcomes when I don't replace the ball. Okay. All right, so this next one, you want to create an ID code for all your customers based on 3 characters. The first character must be a letter of the alphabet, and the second and third must each be a digit between 1 and 9 inclusive. How many codes are there? Would either of the methods be practical in this case? Using the patterns you noticed in the previous problems, what is your best guess? So how many codes? Well, we'll figure it out. Okay, so 3-digit code. Okay, so the first digit has to be a letter of the alphabet. So I know there are 26 letters in the alphabet. Hopefully. Yeah, 26 letters. And the second and third must each be a digit between 1 and 9, inclusive. So that means including 1 and 9. So if I count 1, 2, 3, 4, between 1 and 9, there's 9 digits. Be careful because if 0 were included, there'd be 10. So there's 9 digits for each of these, assuming I can repeat a digit. So all I have to do is pull up my handy dandy calculator and multiply 26 times 9 times 9. And I get 12,106 different codes. All right. All right. Now, would either of the methods used be practical? Okay, so we're talking about the tree diagram and the table. And the answer is for the tree, no, because you're going to have 26 branches followed by 9 each. I mean, that would be, you know, you'd have to draw 2,106 branches. So it's not practical. For the table, you're comparing 3 things, not 2 things, and it'd be a 26 list long table, and it's no. So definitely not practical. So that's why the multiplication principle comes in. Okay, things you should know for probability. All right, the sample space is the list of everything that you are considering. All right, so it's every possible outcome in an experiment. So if I'm flipping, you know, a coin twice, I've got 4 possible outcomes, right? Heads, 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 tails, tails, heads, tails, tails. So every possible outcome, and it is the set of every possible outcome. So like the sample space for flipping 2 coins, write it this way. That would be my sample space, okay? So an element is a member of a set. So for example, HH would be a member of that set. Oh, no brackets around members though, only sets, okay? All right, a set is a collection, a well-defined collection. All right, an outcome is basically an element of the sample space. An outcome is something that can happen, right? It's a result of an experiment. It's a member of the sample set. I'll just write SS for sample set. All right, and a subset is a set, so it needs the brackets. It is every element is in its corresponding set. So if I were to list a subset, you know, of the thing above, HH, HT, whatever, that's a subset. Remember that the empty set is a subset of every set. And a proper subset, it can't be equal. So if I wrote all 4 of them down, that would be a not proper subset, okay? Okay. So we didn't have quite time to get to all this stuff. Well, let's get to this, and then we stopped, and I'm probably gonna make it just another video. So it says a standard 6-sided die is cast. Then a 3-color red, blue, and green spinner is spun. Draw a tree diagram with all the outcomes in a set. Give the sample space, okay? And 4 different subsets. Okay, so I'm spinning a die, so I know that the die can get the numbers 1, 2, 3. You want to make these big enough so you can write 4 or 5. We have 6 branches, right? You can read that, 3, 4, 5, 6. All right. Colors: blue, red, blue, green. Red, blue, green for each of these branches. Red, blue, green. Red, blue, green. All right, so then to get the sample space, I would have to look down the branches and list every single element in there. So like, I'm gonna start this, probably not finish it. So like a 1 in a red spinner, a 1 in a blue spinner, a 1 in a green spinner. So I'm just reading down the branches. This would be 2 red, 2 blue, 2 green, and you get the picture. Okay. All right, so so that's kind of how a tree works. All right, so what do they want? List 4 different subsets. So they have the empty set, that's a subset. Any combination of these things is a subset. So my pen just died. All right, so we'll do All right, so it doesn't really matter, you know, it could be one red, one green. You get the idea, right? The subsets, any combination of these. 2 red, 2 blue. Okay. All right, so there's many subsets. In fact, if I include the improper subset, there's 2 to that. Let's see how many elements are in this thing. Well, let's figure that out. Why not? How many outcomes? Sorry. Well, it looks like there's 6 times 3 of each of those. So 6 times 3, red, green, or blue are one of the 6 roles. So there's 18 possible outcomes to this experiment. So if you wanted to know the number of subsets, it's just, so the number of subsets is 2 to the 18. All right, because it's either in there or it's not. All right, so a lot of subsets. All right, I'm gonna stop the video here because this is where we stopped on Thursday. I think I'll probably start, I'll make another video for Monday. Let's do it that way. All right, so I'm gonna stop this here and we'll pick up in the other section. Did I record it?